Okay, here I'm going to be looking at aromatics and halogen-based hydrocarbons, or halides, if you will. And really, I'm going to talk about their naming, but there's not much new to the naming. It's mostly the same as the rules for the side chains that we're talking about, so I really just want to talk about what these things are. So an aromatic is a carbon that when this string of carbons starts to form, it starts to bend backward and actually forms a ring structure where it attaches back onto itself. So here we can see a 6 carbon ring and a 6 carbon ring, even a 5 carbon ring, are long enough that they can actually get turned around and form a ring instead of a chain-like structure. When that's the case, the naming, when there's nothing else going on, isn't all that difficult. If this would have been hexane, if it didn't branch back onto itself, now we call it cyclohexane. And when we're dealing with these and we have things like side chains, let's say for example that I had a side chain here, then I can choose any carbon in this circle to act as carbon 1. So I always do that to keep the numbers as low as possible. So this would be 1-ethyl cyclohexane. So that's a basic idea of an aromatic. There's all kinds of aromatics. When you look at organic structures, you always see these ring structures forming. But there's one aromatic that's a little bit special, and that aromatic is called benzene. Benzene is a 6 carbon ring with alternating double and single bonds. So here we can imagine that each one of these carbons is an sp2 or a trigonal planar hybridization. What that means then is each one of these angles would be like 120 degrees, with the third spoke on the 120 degrees holding a hydrogen atom off in the same plane as the molecule. So this isn't an oversimplification. This is what this molecule would really look like. It'd be two-dimensional, forming this hexagon, this perfect hexagon with these hydrogens going off. And what's important or sort of interesting about this is that if we imagine the pi bond formed between neighboring molecules, there'd be a pi orbital that goes above the plane of the page and one that goes below the plane of the page. And this would be true for every carbon atom in the molecule. What that means then is that below the page there would be this giant orbital ring that's formed with these pi molecules, and above the page there'd be this giant orbital ring that's formed with these things, almost like two donuts resting above and below the molecule. The reason that this is important is that this double bond is not considered to be localized, but instead is considered to be a delocalized bond shared throughout the entire molecule. So when I originally drew this, I went C single, C double, C single, C double, implying that some of these bonds are double bonds and some of them are single bonds. But when we actually draw this molecule, sometimes we draw it like this. And then to indicate the double bond, we put a circle going all the way around, because it isn't like the double bond exists here, but not here. This double bond is delocalized through the entire molecule and shared all the way around. What's interesting then about this molecule is that it becomes very stable, especially for a molecule that contains a double bond. So usually when you have a double bond, that's an opportunity for halogenation or other things like that we're going to talk about later. But in this particular case, this molecule is very stable and becomes a common component in a whole lot of organic compounds because it's stable and has interesting properties that we're able to exploit, but also cause it to naturally occur quite a bit. So that special molecule is called benzene. And it's probably the most common of the aromatic compounds that we're going to see as we look through this. Halides are the idea that you have a carbon chain where one of the hydrogens has been replaced by some halogen. And if we think about it in the sense of this particular bonding, the halogens with their 7 valence electrons and their ability to form one covalent bond behave a lot like hydrogen would. And so that halogen can take the place of a hydrogen in the molecule. That's what makes it a halide. We're going to talk about their properties more in a subsequent video. For now, we're just going to really focus on what they are and how we name them. So in this case, we name the halogen as if it was a side chain. It follows all the other same rules that we talked about with side chains, and the prefixes associated with these are fluoro, chloro, bromo, and iodo, respectively, to the halogen molecules. So this, for example, with its 4-carbon chain, would be butane. And representing its bromine, which you might want to put on 3, but if you go from the right-hand side, it's really on 2. That's the lowest we can get that number. So this would be 2-bromobutane. We can, the halogen will never actually cause the main chain to branch like it does with a carbon side chain, but the same rules with regard to double bonds needing to be included and multiple of these halogen groups being represented by putting dibromo or tribromo, as well as the ordering that you put them in being alphabetical, still follows from the side chain rule. So we'll just do one more example here before we stop this video. Let's imagine we got pentane, we got 2 Cls on it, and what the heck, let's put a fluorine group here. One thing you can do if you get tired of writing hydrogen all the time is if you put a dash and you put nothing at the end of it, it's assumed that it's a hydrogen. So I might start using that little shortcut from time to time here. So here I've got a pentane. And it doesn't make any difference if I go from the left to the right, so I'm going to go from the left to get the lowest numbers for the 2 chloros. So I'm going to get 2, 3, dichloro, 4, fluoropentane. So you can see it's following the same rules. The fluor comes after the chloro because F comes after C. And other than that, it's following the same basic side chain rules for naming, and that's indicating that a halogen has taken the place of one of the regular hydrogens in the normal carbon chain.